Hey everyone, welcome to Star Talk. We're thrilled to have you here with us today. Today, we're tackling a question as old as time, well, almost. It's a question that has puzzled and fascinated humans for centuries. Why does light seem to travel faster than sound? You know it's true, but have you ever wondered why? You see the lightning flash before you hear the thunderclap. This phenomenon is something we've all experienced during a storm. First things first, what are light and sound? Let's break it down to understand the basics. Light is how we see the world. It's the reason we can perceive colors, shapes, and movements. It's made of tiny packets of energy called photons. These photons are the fundamental particles of light. These photons travel in waves like ripples in a pond. Imagine throwing a stone into a still pond and watching the ripples spread out. Sound, on the other hand, is all about vibrations. It's the result of objects vibrating and creating waves in the air. When something vibrates, it makes the air around it vibrate too. These vibrations then travel through the air. These vibrations travel to our ears, and we hear them as sound. Our ears are finely tuned instruments that can detect these vibrations. So, light is about energy traveling in waves. These waves can travel through the vacuum of space, which is why we can see stars light years away. Sound is about vibrations traveling through a medium like air or water. Unlike light, sound needs a medium to travel through. But why the speed difference? Let's dive deeper. Light travels at an astonishing speed of about 299,792 kilometers per second in a vacuum. Sound, however, travels much slower at about 343 meters per second in air. This difference is due to the nature of how light and sound waves propagate. Light waves are electromagnetic and can travel through the vacuum of space, while sound waves are mechanical and require a medium to move through. The density and elasticity of the medium also affect the speed of sound. For instance, sound travels faster in water than in air because water molecules are closer together, allowing vibrations to transfer more quickly. Understanding these fundamental differences helps us appreciate the unique characteristics of light and sound.
Here's where things get really interesting. Light and sound travel in waves, but the types of waves are fundamentally different. Light is an electromagnetic wave. It doesn't need anything to travel through. It can even zoom through the vacuum of space. Sound, however, is a mechanical wave. It needs a medium to travel, like air, water, or even a solid object. Think of it like this. Sound is like a message passed from one molecule to the next. No molecules, no sound. This fundamental difference in how light and sound travel plays a big role in their speeds. Let's talk numbers, shall we?
Light speed is the ultimate speed limit in the universe. It's the fastest anything can travel, and it's a fundamental constant in the world of physics. In the vacuum of space, light travels at a mind-boggling 299,792,458 meters per second. This speed is so immense that it's hard to even comprehend. That's about 671 million miles per hour. To put that into perspective, if you could travel at the speed of light, you could circle the Earth more than 7 times in just 1 second. It's so fast that we use it to measure the vast distances in space, like light years. A light year is the distance light travels in 1 year, which is nearly 6 trillion miles. This unit helps astronomers and scientists understand the immense scale of the universe. Now, you might think light always travels at this speed, but there's a catch. The speed of light can change depending on the medium it travels through. When light passes through different materials, like water or glass, it slows down a bit. This phenomenon is known as refraction. For example, in water, light travels at about 75% of its speed in a vacuum. But even then, it's still incredibly fast. Even in the densest materials, light still moves at speeds that are hard to fathom. So, light is a speed demon, zipping through the universe at the fastest speed possible. But what about sound? Sound travels much slower than light. In air, sound travels at about 343 meters per second, which is less than a millionth of the speed of light. This is why we see lightning before we hear the thunder. The light from the lightning reaches us almost instantly, while the sound of the thunder takes longer to travel the same distance. Understanding the speed of light not only helps us grasp the vastness of the universe, but also plays a crucial role in technologies like GPS, telecommunications, and even medical imaging. It's a universal constant that continues to fascinate and inspire us.
Sound is a bit more laid back than light. In dry air at room temperature, sound travels at a leisurely 343 meters per second, or about 767 miles per hour. That's still pretty fast, but nowhere near the speed of light. Here's the thing about sound speed. It's not constant. It changes depending on what the sound is traveling through. Sound travels faster in water than in air, and even faster in solids like steel. Why the difference? Remember, sound needs a medium to travel. The denser the medium, the closer together the molecules are, and the faster they can pass those sound vibrations along.
We've seen the numbers, but what's the underlying reason for this speed difference? It all boils down to those pesky laws of physics. Light, being an electromagnetic wave, is made up of massless photons. These photons don't have any mass, so they can zip around at the universe's speed limit without breaking a sweat. Sound, on the other hand, relies on the vibration of molecules. These molecules have mass, and it takes time and energy to get them moving. The heavier the molecules and the weaker the bonds between them, the slower the sound travels. So, light's lack of mass and sound's reliance on massive particles are the key factors behind their speed differences.
Let's talk about a real-world example we've all experienced. Lightning and thunder. You see the lightning flash first, then you hear the thunder rumble a few seconds later. Why? Because light travels about 1,000,000 times faster than sound. The lightning flash and the thunderclap happen at the same time. But because light reaches your eyes almost instantaneously, while sound takes its sweet time traveling through the air, you experience them as separate events. This delay between the flash and the bang is a perfect illustration of the speed difference between light and sound. It's a cool reminder that even though we perceive them together, they're traveling at vastly different speeds.
This difference in speed isn't just a cool scientific fact. It's a fundamental aspect that shapes our understanding of the universe and influences various technologies we rely on every day. It has real-world implications in technology and science. Take telescopes, for example. These powerful instruments have revolutionized our ability to observe the cosmos. Telescopes allow us to see distant stars and galaxies, providing a window into the past and helping us understand the history and evolution of the universe. But the light from those objects takes time to reach us. This delay means that when we observe celestial bodies, we're actually looking back in time. So when we look at a star that's thousands of light years away, we're actually seeing it as it was thousands of years ago. This concept, known as the look-back time, is crucial for astronomers. That's because the light from that star took thousands of years to travel through space and reach our telescopes. This phenomenon allows scientists to study the early stages of the universe and gain insights into its formation and development.
Then there's ultrasound technology. Doctors use ultrasound to create images of the inside of our bodies. This non-invasive technique has become a cornerstone in medical diagnostics. They work by sending sound waves into the body and measuring how long it takes for those waves to bounce back. The speed of sound in different tissues helps create detailed images. This information helps them create images of our organs and tissues. Ultrasound is particularly valuable for monitoring pregnancies, diagnosing conditions, and guiding certain medical procedures. These are just a couple of examples of how the different speeds of light and sound have led to important technological advancements. From exploring the vastness of space to peering inside the human body, understanding these speeds has opened up new frontiers in both astronomy and medicine. The implications of speed extend beyond just light and sound. They influence everything from communication technologies to transportation systems. For instance, the speed of electromagnetic waves is crucial for the functioning of our internet and mobile networks. Fiber optic cables, which transmit data at the speed of light, have revolutionized how we share information, making global communication faster and more efficient. In transportation, understanding speed is essential for designing vehicles that can travel faster and more safely. High-speed trains and advanced aircraft are examples of how speed considerations drive innovation. As we continue to push the boundaries of speed, we unlock new possibilities and face new challenges. The quest to understand and harness speed is a testament to human ingenuity and our relentless pursuit of progress. So the next time you think about the speed of light or sound, remember that these aren't just abstract concepts. They are the driving forces behind some of the most remarkable achievements in science and technology.
So there you have it. Light travels faster than sound because it's an electromagnetic wave made of massless photons that can travel at the universe's speed limit. Sound, on the other hand, is a mechanical wave that needs a medium to travel, and its speed depends on the properties of that medium. This difference in speed has some pretty amazing implications, from how we understand the vast distances in space to how we use sound waves to see inside the human body. Keep those questions coming and remember to keep looking up, to keep